Okay, now we're really going to get into how we harness this electricity from redox reactions. Okay, so essentially it's really just batteries. And how we do this. So what we're looking for is, and these are called voltaic cells or galvanic cells. You will hear and see both terms used, they mean the same thing. So we're looking for spontaneous or favored reactions where the electrons transfer from a more active metal to a less active metal. That is the whole goal of voltaic cells, okay? Because that's going to happen spontaneously. Like that reaction that I used in the first video, if you put a piece of zinc into copper 2 chloride, which is what is going on here, these are going to spontaneously react, okay? The zinc is going to turn from zinc into Zn2+, and the copper is going to go from Cu2+ to actual solid copper. This is a spontaneous reaction. I just stick a piece of zinc in here and that's what you get. You get solid copper out of it. Okay, so that is spontaneous and we want to harness the energy associated with that electron transfer. Okay, so how can we harness this electron transfer and use it for energy? So essentially what you have to do is if we separate the two half reactions, then we can actually use that flow of electrons to get electricity. So if you've ever taken physics or any type of physical science before, essentially anytime you have moving charges, that is electricity. And if we can use those moving charges, then we can actually use that electricity. So anytime you've got moving charges, you're conducting electricity. So a voltaic, or like I said, galvanic cell produces a positive voltage. So when we're talking about voltaic or galvanic, these are things that are spontaneous. I don't have to put in energy for them to happen. They react by themselves and we get energy out of them. Okay, so this is our cell. This is a voltaic or a galvanic cell where we have separated the two half reactions. I'm going to talk through each of the parts of this. Okay, so there is an anode and a cathode. The oxidation part takes place at the anode. The reduction part takes place at the cathode. Okay. If you remember from 161, all cats have pause. Cations are the positive part. And the other phrases I have at the bottom of this page for oxidation, it is anox. So anox is anode is oxidation. And Leo the lion says grr, and he is a red cat. Means reduction occurs at the cathode. That's how we remember that the anode is oxidation, anox, and reduction occurs at the cathode, means a red cat. Okay, so when I'm labeling these, I would be like, okay, this is my cathode. That is where reduction is happening. This is my anode. This is where oxidation is happening. So zinc being oxidized, copper being reduced. Okay, now the flow of electrons then is always going to go from the anode to the cathode, because something is losing electrons and something is gaining electrons. Wherever we're losing the electrons, so the zinc is losing electrons when it's going from Zn0 to Zn2+. They are going to flow to the cathode, which is where we are going to be gaining the electrons. So the copper 2+ is going to be taking in those electrons, making copper no charge, which is copper metal. And that's how we get the copper metal to be on the right side. Okay, so you should always have something connecting them. This is our anode, this is our cathode. Electrons will be flowing from anode to cathode. Okay, now a couple other things in this process. You have to have a salt bridge. This is our salt bridge. Usually we use sodium nitrate or potassium nitrate just because those don't usually interfere with anything and they're completely soluble. But you have to have a salt bridge so that ions can flow to actually balance out the charges. If you think about it, as I continually make more Zn2+ here, then I'm going to end up with like a really positive solution over here. And if I'm continually using up my copper 2+ over here, I'm going to end up with a really negative solution over here. And the universe is not happy with that. You can't have just a beaker of positive ions. It's very, very unstable. It's not going to happen. So we have to have a salt bridge where these ions, so the nitrates and the sodiums, can move back and forth to just kind of balance out that charge. So as I'm creating all of these Zn2+ on the right side, I need something negative to come over there to just balance out that charge. So these nitrate ions are going to flow this way to kind of balance out that charge. On the right side, as I'm using up those Cu2+ to make copper metal, this is going to start to get really negative. So the Na+ ions are going to flow this way to make sure that that charge gets balanced out. So a salt bridge is necessary in order to actually conduct electricity. Okay, so these are my mnemonics, right? I think that's how you spell mnemonics. Anox, anode oxidation, red cat reduction, cathode. Leo the lion says GR, losing electrons is oxidation, gaining electrons is reduction. So if you don't know where the electrons are going, these should hopefully kind of help. Okay, so this is a little bit of like a close-up view. I like looking at the molecular views of what's going on with these, because you might be like, well, if you stick, or right, we were looking at this picture earlier. If you actually stick a piece of metal in there, we end up with copper, and actually solid copper that has a mass. So it almost looks like you're creating mass. You are of course not, according to the law of conservation of mass. We're just turning something that was in the solution into solid. Okay, so what you will notice is, yes, copper is going to plate or deposit onto that copper plate, but you're also losing zinc. Okay, so on the molecular level, if you look at this little picture, the zinc molecules, which were solid, are turning into ions. So they're popping off of the solid and dissolving essentially as they turn into zinc 2 pluses, because that is soluble. So you end up with a zinc anode that has lost all of this mass, and it's just because now it's in solution zinc 2 plus. Whereas on the other side, those copper ions that were floating in the solution are turning into copper metal and depositing onto this cathode. So we actually end up with copper on the cathode as this reaction happens. Okay, this is a way that we kind of denote what the cell looks like. So instead of drawing out the whole thing, this is the notation for a voltaic cell. You always list the anode first and the cathode second. And so what you do is you write whatever the anode is, that solid is zinc. Okay, got zinc, which changes into Zn2 plus. And it goes in like the process. These are reactants. These are the products, okay, of what is happening in the reaction. So if you can't remember essentially like what order these should be in, they should be in the reactants to the products. Okay, zinc turns into zinc 2 plus. Okay, this is solid, this is aqueous. Usually you put your molarity here as well. And then you write 2 lines to represent your salt bridge. Okay, and then on the right side, we have copper turning into copper solid. Cathode should be listed last. So again, these should be in order of what's happening in the reaction. The Cu2 plus, which is aqueous and has some molarity, is turning into copper solid. So this is like the way that the equation is going. Zinc solid to zinc 2 plus, copper 2 plus to copper solid. Always list the anode first. This phase boundary just means like this was the solid and this is the solution. So this is going to show you essentially what is going on in a voltaic cell.